Hello everyone. So today what I'm going to talk, I'm going to not get into the depth of performance analysis. That's altogether a huge topic. But what I'm going to do today is introduce a tool which I got to know recently. It's called as a flame graphs. And I will go through that. Okay, without flame graph, what are the basic steps to do a performance analysis? And when you get hold of flame graphs, how things become easy. Okay, so what I'm going to cover is basically, just give an introduction about what are profilers, what they do. Then we'll talk about perf event, which is one of the profiler available on Linux system. Then we'll go through like what is a flame graph, how do you generate a flame graph, and then at the end we'll see that okay, how you can use this flame graph not just for performance analysis but for other data visualization or any visualization, if that caters to your solution. So let's start. So what are profilers? Profilers are nothing but a set of tools to collect the performance data. So these tools collect the performance data from let's say hardware interrupts, hardware performance counters. They do a code instrumentation and again try to collect the data. They are basically event based, some are sample based, right? So different profilers are available for different use cases on different operating systems. For example, Windows you will get different set of profilers, whereas on let's say Mac OS you get dtrace and other profilers. On Linux, perf event, or it's also called as perf, is a very familiar, very popular tool to do this performance analysis. So let's we'll focus today on the Linux side. Um, so Linux provides one performance tool called as a Linux perf tool. It was originally called as performance counter for Linux, also Linux perf events. So if you want to go and search, and if you try to just search for perf, you might not get the desired search result. So you can search for perf events or something like that. What it does, it basically provides many subcommands to trace multiple things. You can trace, let's say, C functions. You can trace hardware events like, let's say, D cache misses, L1 cache misses. You can context switches. All different kinds of such events can be measured there. Okay. Then you can also trace the K probes and U probes. I haven't used with K probes and U probes, but yeah, basically U probe is to K probes and U probes are for dynamic tracing of user code and kernel code, whereas trace points are kind of static tracing. So let's talk about a little bit about how do you use this perf tool. So as I mentioned, it provides different subcommands. So for example, one subcommand is a stat. What does the stat subcommand does is basically it counts the number of events. It doesn't record anything other than that. For example, if you want to count that how many times, let's say, a malloc function got called, then you can just use perf stat and -uc malloc to basically check how many number of times that malloc is called. And you can do this tracing on a particular process by using a command or by using a process ID, or you can do system wide tracing. Whereas the perf record just doesn't only record the statistic, but it records the sample data. Okay, it records the call graph and other details as well, and it records in a binary format. The perf report tool, what does it do? It basically, whatever you have recorded using a perf record, it analyzes that binary format and displays it in different forms. One form is, let's say, just a text form. Another in is this text terminal based interface is called as TUI. And the another subcommand is list, which basically tells you that what are the available events to trace. There are more subcommands, so this is generally popular subcommands which are used by most of the people, so that's why I included here. You can go and find more information about this on the given two links. So let's take an example of perf tool here. For example, if I want to record CPU functions at 99 Hertz, so what I just do, perf record minus F99 and command. Let's say I want to record it for 10 seconds only, and specifically I want to use the DORF information, debug DORF information. So I can just say, okay, generate the call graph using this DORF, and slip 10 means, okay, just record for 10 seconds and then terminate. If you want to do recorded data for the complete system, then you can pass -a flag. And here what I am saying here is this event is, let's say, L1D cache load misses. So you record the call graph on every 10,000 occurrence of L1D cache load misses. So not on every count of L1D cache load misses, but on every 10,000. So that's what I am interested might be, right? Let's say you want on every L1D cache load misses. Yeah, you can just say -c is equal to 1. Once you record data, generally it is recorded in file called as perf.data. Okay, and then you can basically analyze that using a perf report. And if you want to go inside assembly and annotate the assembly code, and that you can basically do it using perf annotate data study IO. Let's say on terminal only you will see this annotation, and there you can see at assembly level the performance. So all these above examples you can again find, there is a nice write-up on this website, and so let's see one example, live example I'm going to show you here. So for example, I'm using one of the JSON parsing library, and I'm going to parse a very large JSON file, about 23 MB, and let's see, how does it records the perf data and how do we visualize that one. So for example, if I just say perf record, so what I'm doing is I'm recording at 99 Hertz, -g means call graph, and I'm recording for this command. So this is parse JSON program which I have written, and let's see what it generates. Okay, so the program started, perf started recording the data. Yeah, so it basically recorded approximately 781 samples in this file called as perf.data. We can just see here we have this perf.data generated right now. Now what I can do, I can just use this perf report tool. Okay, so it has different options. Let's say let's go with the default options. Okay, so you see, it is analyzing this one, and it is reporting the percentage here. Now this percentage is not the time spent, it is basically the percentage of number of samples. So we can see that, okay, main function including its children is accountable for 96.95% of overhead. So basically including the children, you are saying 96.95%. So this is useful, let's say, if you want to find out, okay, which higher level function is causing a more overhead. So let's say main, we are not interested, yeah, but let's say this operator, right, there is some output O stream operator which is overloaded, which is almost, this is a higher level function which is causing almost 30.64% overhead here. Okay, you can get into the details that, okay, out of this which function is causing what to one. So basically this operator is implemented using something serializer function, and then there is another serializer call and another serializer call. So it has a different set of calls, and you can see at each level what is the overhead. Now this gives an idea about the higher level function. Now let's say you want to find out overhead of particular function, right? Because what earlier was including parent and their children. So if I just pass no children here, so now here we can see that okay, the individual functions and their overhead, and it doesn't include their child's overhead, right? So here you can see this par JSON, this lexer function is accounting for almost 7% of data, right, or 7% of sample size. And if you go inside, you can just also find out okay how from where this parse, or sorry, the lexer function is getting called. So basically from main there is JSON parser lexer, and this is the call hierarchy. Okay, this is good. I mean, if you have a very small applications to run and do a performance analysis, this is good. Let me just show another. So basically, if I want to, let's say, show this report in another format, because let's say I have a very huge application where each different component of application is a dynamic library, a separate dynamic libraries, and then I want to show that okay, what different portion of that code or my complete system is consuming more CPU. So for example, here I didn't have any dynamic library, but yes, we had libc, then the program itself, and then libstdc++. So you can see almost 40.37% is from libstdc++, and again it's includes the children as well. And obviously par JSON is 96.95% because it is the program which is the complete one, so almost near about 100%. And you can see libc is 99% because we know that main function is called from libc, like let's say libc start main and that, right, and then from we call a main function. That's why we don't see a 100% for this main one. Okay, this is good, but doing this kind of analysis is not that straightforward, and deriving about like okay, which are higher level functions which are using so much of CPU, and then their call stack, it's a little bit cumbersome. So that's when this flame graphs come in a picture. So let me go back to PPT. So now what is a flame graph? So I have taken this definition as it is from the creator. So flame graphs are a visualization of hierarchical data. So remember, this is a hierarchical data created to visualize track traces. Not necessary that we want to always visualize track traces. We can visualize any hierarchical data of a profile software so that the most frequent code paths to be identified quickly and accurately. So let's see how this flame graph looks like. So this is how generally a flame graph looks like for a particular profile program. So here you can see, so let me explain that what is this flame graph means. So on x-axis you have a call frames, or sorry, this stack frames, and on y-axis basically you have the samples, right? So if I say now the wider the call the stack frame is, the more sample it basically has, so more number of time it has occurred in the stack frame, right? Don't worry about these colors are like kind of random. Color doesn't say that okay whether a particular thing was using high CPU or low CPU. So what says basically, for example, if you see main, you can see main almost swapping around 95-99%, and there are some unknowns. So that means every time we have sampled the program, main was on call stack. Okay, so this is what it shows. So we'll generate one flame graph and we'll see or we'll go into the details of that one as well. Basically y-axis is the stack depth, so counting from 0, let's say 0 1 2 3 4 5. Okay, so that's what I have mentioned here. X-axis is nothing but stack profile population. Again, this is sorted alphabetically, so it has nothing to do with the time. Basically it is the number of samples, based on the number of samples which it has collected. Y-axis stack depth counting from 0. Each rectangle represents a stack frame, and the wider a frame is the more often it was present on a stack. So let's say now we want to generate such a flame graph. How do we generate it, and what inference we can do from that flame graph? So basically, generating any flame graph is a step approach. Basically, you capture this stack, and now we are capturing here a plain stack. You just want to capture stack on, let's say, event of malloc, just to find out okay, the memory leaks might be, or how program is allocating memories, or let's say using realloc, or let's say brk system call, right? So on all that event you want to record that stack, so you can modify this perf record command accordingly. So once we get this perf.data file, what we have to do, we have to represent it in a particular format. It's called as a stack collapse format. I will cover that format at the end. And in that format, basically what you do, so there are a bunch of Perl scripts available into the same Flamegraph repository. So I think I haven't included the Flamegraph repository path, but you can always go and visit this link. Braden Greg, who is the creator of Flamegraph, bradengreg.com/flamegraphs.html, where he has listed the steps and from where to clone the repository as well. So now that repository contains basically these different scripts for, let's say, stack collapsing. And the good thing about this flame graph is it is independent of profiler, and it is not meant only for C++. You can use it for JavaScript, Java, for any programming language for which you can collect a call stack. So once you create the collapsed stack, you can just pass that collapsed stack to flamegraph.pl, which is a Perl based tool, and it will generate a SVG format image. And the SVG format image is interactive image. We will see how it looks like and what we can do that with that image. So basically there are different types of flame graph which are supported. One which we were looking for a CPU. Let's say for memory you want to find out, yeah, you basically need to change the perf record command. There is nothing special in the memory. Whereas this op CPU is basically what you want to do is you just don't want to record let's say something for what is executing on the CPU, but for something as well which is waiting for some event to happen, let's say IO event, and that. So that wait time you might want to, let's say, check, because if that waiting is synchronous, then the performance might get affected. Hot and cold basically combine CPU and off CPU. The interesting one is this differential one. I thought of basically, having all these graphs shown here, but unfortunately my Linux system was not working. So I'm just mentioning their types. So what is this differential is basically you have some repository as of now, you record a baseline version of flame graph or the call stack, then you do some changes, and then once again you record and you generate it, and now you want to compare these two graphs side by side. So in that case this differential flame graph comes in a picture. So how to generate all these flame graphs, you can go and visit the website, you will find tutorials there. Now we'll come to this creating custom flame graph later on. Let me just show how the generated flame graph looks like. So due to the lack of time, I'm not going to generate it, but you can assume that okay, I have generated it, or let me just generate it. Take a lot of time. So we have this perf.data. What we want now, this collapse thing. Okay. So okay, the collapse thing is done now. And now what I want to generate is flame graph, right? Say flamegraph.pl, and that's it. For example, this perf underscore x.svg is generated now. So you can just see the timestamp. Yes, it is generated now, and if I open it, yeah, right. This is because I use another file to generate it. Basically, what I used is format.folded. We'll come to that one later on. So let me just use the one which was generated, this out.perf.folded, right? Okay. Just let me check what is happening. Okay, so basically want to do first collapse and yes, we have it. Then we want to generate a flame graph. Okay, 1122. Oh, okay, so I'm loading a wrong one. Yeah, sorry, I was loading wrong one. So you can see the flame graph generated here only, right? So what are the other functionality which is provided by this interactive flame graph is basically what you can do. You just want to just explore one of these call stack. So let's say from here you want to explore, so you can just zoom in. So now other things are hidden. Let's say you want to go into this path, other things are hidden. And this is what you can basically do. And the another thing is, let's say if this call stack is too big, so what you can do, you can just do Control F and try to find out something. For example, I'm trying to find out, let's say, std vector. So wherever there is std vector, it has highlighted using a purple color. Okay, so these are some things which is supported by these flame graphs. Okay, so let's say going back to the last section, which is nothing but creating custom flame graph. So as I mentioned, this flame graph is independent of any profiler. It expects input format in a particular given fashion, and if it is there, then it can just generate a flame graph. So the format is basically collapse stack. So basically, let's say you have some hierarchical data, you just put that hierarchical data in a semicolon. So now you can put your name, my name, anything, any data here, separated by semicolon. And let's say this is one stack we are seeing. If this complete stack is, let's say, I have observed 100 times, so I will just mention here is 100. This stack is around 30 times, and this stack is around 20 times. Now while generating the call stack, what it will do, it will try to merge this stack as well. For example, you can say main, okay, the below one, the main layer will get started, and then B will get collapsed. By side of that there will be A. Then you can't collapse any one of these things, right? Or you can't merge these things. So this is how the frame graph will look like. For example, the one which was showing earlier. Fully, yes. Okay, sorry. So I have some different format which I have used here. Let me show that one as well. Oh, everything is different. So let me just say I want to generate a flame graph from this format dot folded, and should be there now. Yeah, so here it is, right? So main is collapse, and then A and B are side by side. You can't basically merge other B, A, and C. So this is how it looks like. And if you see that, okay, the main, we had 150 calls. So basically, if you try to combine that 130 and 20, it was basically main was appearing everywhere, so 150. So this is how this flame curves thing works. That's it from my side.